Okay, so the third example is going to be taken as a kind of geometry problem. I'll draw a picture of it. Suppose you have a curve with the following property. If you take a point on the curve and you take the ray from the origin to the curve. Whoops, well, that's not going to be the one that I want. I think I'm going to want something which is steeper, because what I'm going to insist is that the tangent line be twice as steep as the ray from the origin. So in other words, slope of tangent line equals twice slope of ray from origin. All right, so that's the slope of this orange line is twice the slope of the pink line. Now, these kinds of geometric problems can be written very succinctly with differential equations. Namely, it's just the following. dy dx, that's the slope of the tangent line, is equal to, well, remember what the slope of this ray is if this point, I need a notation, if this point is x comma y, which is a point on the curve. So the slope of this pink line is what? Y over x. So if it's twice it, there's the equation. Okay, now, we only have one method for solving these equations. So let's use it. It says to separate variables. So I write dy divided by y here is equal to 2 dx divided by x. That's the basic separation. That's the procedure that we're always going to use. And now if I integrate that, I find that on the right-hand side, I have the logarithm of y. And on the left-hand, on the left-hand side, I have the logarithm of y. On the right-hand side, I have twice the logarithm of x plus a constant. So let's see what happens to this example. This is an implicit equation, and of course we have the problems of the plus and minus signs, which I'm not going to worry about until later. So let's exponentiate and see what happens. We get e to the log y is equal to e to the 2 log x plus c. So again, this is y on the left-hand side. And on the right-hand side, if you think about it for a second, it's e to the log x squared, which is x squared. So this is x squared, and then there's an e to the c. So that's another one of these a factors here. All right? A is equal to e to the c. So the answer is, well, I'll draw the picture. And I'm going to cheat as I did before. We skipped the case y negative. We really only did the case y positive so far. But if you think about it for a second, and we'll check it in a second, you're going to get all of these parabolas here. So the solution is this family of functions, and they can be bending down as well as up. So these are the solutions to this equation. Every single one of these curves has the property that if you pick a point on it, the tangent line has twice the slope of the ray to the origin. And the formula, if you like, of the general solution is y equals ax squared. A is any constant. Question?
I'm not quite sure how A can be made. I mean, I see that it could be in your graphical representation, but ln, you can't allow a negative number, right?
Yeah. So again, so first of all, one thing, so there are two approaches to this. One is to check it and make sure that it's right. When a formula works for some family of values, sometimes it works for others. But another one is to realize that these things will usually work out this way. Because in this argument here, I allowed the absolute value. All right? And that would have been a perfectly legal thing for me to do. I could have put in absolute values here. In which case, I would have gotten that the absolute value of this was equal to that. And now you see I've covered the plus and minus cases. All right? So it's that same idea. This implies that y is equal to either plus ax squared or minus ax squared, depending on which sign you pick. So that allows me for the curves above and the curves below.
Why couldn't you just insert the absolute value?
Because it's really true that the antiderivative here is this function. It's defined for y negative. So let's just double check. In this case, what's happening, we have the y equals ax squared, and we want to compute dy dx to make sure that it satisfies the equation that I started out with. And what I see here is that this is 2ax. And now I'm going to write this in a suggestive way. I'm going to write it as 2ax squared divided by x. And sure enough, this is 2y divided by x. Now, it does not matter whether it works for a positive, a negative, a equals 0. It's okay. Again, we didn't pick up by this method the a equals 0 case, and that's not surprising because we divided by y. There's another thing to watch out about this example. So there's another warning, which I have to give you. And this is a subtlety which you definitely won't get to in any detail until you get to a higher level ordinary differential equations course, but I do want to warn you about it right now, which is that if you look at the equation, you need to watch out that it's undefined at x equals 0. It's undefined at x equals 0. We also divided by x, and x is also a problem. Now, that actually has an important consequence, which is that, strangely, knowing the value here and knowing the rate of change doesn't specify this function. This is bad, and it violates one of our pieces of intuition. And what's going wrong is that the rate of change was not specified. It's undefined at x equals 0.